Okay, so recording started. Welcome everyone to the presentation of the homework on nonlinear algebraic equations. So in this homework you are going to write two algorithms to find the roots of functions defined by function handles, and then you are going to compare these two search algorithms. So as a first comment here, I would like to mention that a new version of the autograder was posted yesterday sometime in the afternoon, so make sure that you have the last version of the autograder. Also, sometimes the assignment is not clear on the size of the variables that you should use. So make sure that for empty R and FR outputs you have empty arrays defined by brackets. That's when you have an empty R-hist array, make sure that you are defining it with the zeros function, with 0 for the first dimension and 1 for the other dimension, and also make sure that R-hist is a column vector in the output of your functions. So if you don't get the points and you think your algorithm is correct, please check that you have the corresponding definitions for the variables. Okay, so let's start with the first exercise. So in the first exercise, you have to write the function bisect EW7, which implements in MATLAB the bisection methods to find the roots of a function. So the starting point for this exercise is the video bisection method with MATLAB, where Professor Papadopoulos basically gives the code, the basics for the code for this search algorithm. However, pay attention, there are modifications to that code. So first, there is a few checks that you need to do before jumping in the algorithm. So the first check you need to do is that the two boundaries that you provide, XL and XR, are already roots. So if this is the case, if XL or XR are already roots, then you return, so if only one of these are a valid root, you return this number. Otherwise, if both are roots, you return the best approximation. So the best XL or XR. So this is the first check you need to do. The second check you need to do is to check whether the function value at XL and XR have different signs. So if the signs are different, you know that you can find a root. If the signs are not different, so if the signs are equal, it is possible that there is no root in the interval. So in that case, you stop the algorithm, so you stop the function and you return empty arrays. And once again, pay attention to the way you define your empty arrays. Okay, so once that you have done these first checks, you initialize the counter and you initialize the middle points. So the point that is exactly at the half between XL and XR, and you start the algorithm. So pay attention in the while loop. The condition needs to be applied to XM, the middle point, whereas in the video lectures it was applied to XL and XR. So the stopping criterion is different. So make sure that you have the good stopping criterion in your function. So you're going to have a while loop with two conditions. The first condition being that the absolute value of f of xm is bigger than the tolerance in the function. and the other condition in the while loop will be that your counter is still smaller than the maximum number of iterations provided by itermax in the function arguments. So once that you've exited the while loop, you set R to be the xm value, and you set f error to be the corresponding absolute error of the function at the location xm. So once that you've done that, you have to run your function for a few test cases to make sure that your algorithm is running correctly. So the first thing you need to do is to, of course, to define the function handles corresponding to, so you have three cases, right? Three function handles that you need to define. And the second thing I suggest you do is that you plot the shape of the function. So you plot the function on the intervals corresponding to the values of xl and xr, and so thus you can estimate the roots, and you can see if the algorithm finds the roots that you estimated, if everything is consistent. So I've run the test cases. I can write the answers of my test cases for you so that you can see if you have the same answers as I do. Okay, so that was it for exercise 1. So in exercise 2, this exercise is hand-graded. So in exercise 2, you'll have to use the bisect EW7 function to estimate the intersection of two graphs. So the two graphs are defined by two functions, f1 and f2. And what you want to do is that you want to estimate the x values of the points where the two functions are equal. So the first thing you need to do is that you need to define the function handles to the different functions. So you define a function handle to the first function, so to f1 of x. You define a function handle for f2 of x, and you define another function handle to the difference between these two functions. And you want to find the values of x where this the difference between f1 and f2 is 0. And for that, you will use the bisect EW7 function. So once again, I suggest you plot the graph corresponding to the difference between f1 and f2. And in that case, this will be very useful because with the graph, you can estimate the number of roots. And what you want to do in this function is to estimate each root. So the first thing you need to know is the number of roots that you have between 0 and pi for the function defined by the difference between f1 and f2. So estimate the number of roots, then for each root estimate find possible values for lower boundary and an upper boundary of the roots, so for xl and xr. And for that, you can use the grid command to show the grid on your plot, to show a grid on your plot. And it will be easier than to find possible values of xl and xr. So once that you have an estimate of the number of roots, as well as an estimate of the upper and lower boundaries, you are going to call bisect EW7 as many times as you have roots, and each call will give you an estimate of the root. So in this, when you call bisect EW7, you can set the tolerance to be 10 to the minus 6, and the maximum iteration to be something large so that you reach the convergence. So for example, 100. So after that, you'll have an estimate for each of the roots. The last thing they want you to do in this exercise is to verify that the absolute value between the difference of the functions at the location root estimate is smaller than the tolerance. So for each of the root estimates, you can verify that. So that's it for exercise 2. So in exercise 3, you are going to implement another algorithm for root finding. So you will basically implement the Newton-Raphson method. So once again, the starting point for this exercise is the video fixed point method, where you have the structure of the code. So when you write the function, first, same thing, initialize the counter to 0, and initialize the root history to be the starting value x0, which is one of the arguments of the Newton-Raphson EW7 function. So you will begin your estimate at x0. So x0 is the first value in the root history. So once that you initialize that, you can enter the while loop. So once again, you'll have two conditions. And one of the conditions will be that the absolute value of the function at the last root estimate is something bigger than the tolerance. And you can see that the last estimate will be given by the last element of the root history. So you can use rhist end in the while loop conditions. So in the while loop, you are going to compute the new estimates with the equation that is given for the Newton-Raphson method. And you're going to append this new estimate to rhist. Pay attention, rhist is a column vector. And then, so at some point you are going to exit this while loop. And when you exit the loop, the root estimate is the last element of the root history. The error is the corresponding absolute value of the function value at that location. And n, the output argument n, is the number of elements in the root history minus 1. So once again, you have test cases to test that your functions are running correctly. So once again, plot the functions and estimate the roots. Also, to use the Newton-Raphson method, you'll need to define the handles to the derivatives of the functions. So for each function, you'll have to define two handles, the handle to the function definition and the handle to the derivative of the function. And once again, I give you my results here so that you can compare and make sure that you're finding the same roots. Okay, so let's move to exercise 4. So in exercise 4, now that you have implemented the two algorithms for root finding, you are going to compare them. So in 4a, you have a function defined by a polynomial, and you want to find the corresponding roots with the Newton-Raphson method. So first thing, define the function handle to the function and to its derivative. Also, once again, plot the function to visualize where the root is, and you can use also the grid. You can plot a grid to estimate better the value of the root, and then use the Newton-Raphson method to estimate the roots. In 4b, you will be doing exactly the same, but this time with bisect EW7. So for each of the call, you are going to save the root history in two variables. And in 4c and 4d, you are going to make two plots. So in 4c, you are going to first thing to compute the root value with the function f0. So f0 is a function that is already implemented in MATLAB, and with this function you are going to compute the value of the root of the function f, and we are going to do the hypothesis that this is the real value, the real root value. So when you call f0, the first argument, if I remember well, is the handle to the function, and in the second argument you need to provide an interval when you want to find the root. So estimate the interval from the plot that you did in 4a. So once that you know what x star is, so the correct root value, you are going to compute two vectors, being the absolute difference between the successive estimates that you computed in 4a and 4b and x star. So for each value in the root history, you are going to compute the difference between this root and x star. And then you are going to plot the successive differences. So to do the plot, you are going to use a log axis. So this can be done by calling the semilog y function, and then the input arguments are the same than the plot function. So when you call the semilog y is the same as the plot, the arguments are the same as the plot function, and the output argument is only that the y-axis will have log scale. So save the handle for this plot into a variable, and then you will use the handle to write the legend. So you're going to write the legend, and each of the labels will correspond to the functions that you are to the differences that you are plotting. Same thing, you can add a grid and a title to see better what's going on. So in 4D you are going to do the same, but this time you are not going to plot the differences between the root values, but this time between the absolute errors or the function estimations. So you know that at the root the function should be 0. So in 4D you are going to plot the absolute value of the function at locations given by the vector root history. And same thing here, use semilog y to plot a figure with the log axis. So once that you have the plots for 4C and 4D, you'll see that for one of the methods the convergence is faster. So this is what you have to comment in 4E. So basically explain in 4E which of the algorithm is converging faster. Okay, so let's move on to the last exercise. So in the last exercise, we are going to study cases where the Newton-Raphson algorithm, search algorithm, is not converging. So in 4a, you have to use the function bisect EW7 to find the x corresponding to the equation that is given to you. So the first thing you need to do is to define a function handle to the function defined by the difference between the two sides of the equal sign. Then same thing, plot the graph corresponding to this function. And so you know that the x corresponding, so the x that is that satisfies the last equation on page 4 will be the x where the function handle, the function corresponding to the function handle that you have just defined is 0. So the x we are looking for is the root of the function divided by the difference between the two sides of the equal. So we want to find the root of the function. So first thing, we plot the function and estimate where the root is. Then we find initial values for xl and xr, so that are upper bounds and lower bounds for the root estimate. And then you use the bisect EW7 to estimate the root. So then in the rest of this exercise, you are going to use the function arctangent. And what we want to do in this exercise and see for which starting values it is possible to estimate the roots of the arctangent function and for which values it is not. So what you did in 5a, so I'm writing that just as a remark. So what you did in 5a is find the roots corresponding to, so basically corresponding to a point where the problem will be symmetric. So if I write t to be the equation of the tangent at x hat, so where x hat is the solution of the equation, then you can notice that the point where t is intersecting the x-axis is exactly minus x hat. So you can do that because, so you can, to verify that, you can use the function of the expression of the derivative of the arctangent function, which is 1 over 1 plus x squared. So this is exactly what you have on the left-hand side. So the tangent is intersecting the x-axis at minus x hat. So at the next step, you are going to find the equation of the tangent for the point corresponding to minus x hat. And because the arctangent function is symmetric, the next tangent that you are going to find is exactly parallel to the first one. And so because the arctangent is symmetric, you are going, the next tangent are going to intersect the x-axis at location x hat. And so the third tangent that you are going to draw is exactly the first one, and so on. So all the tangents that you are going to draw will be either the first tangent or the second tangent, and the x estimates will be either x hat or minus x hat, and you are not going to converge. So we found exactly the x value where the x estimate are going to be constant from one step to the next. So this will be clearer when you are going to plot the function in 5b. So in 5b, you need to plot the arctangent function. So when you do that, be precise, because you are going to plot the tangents to this function. So the first thing you need to do is that, so you locate on the x-axis the point corresponding to x hat, and then from the value of the arctangent at x hat, you draw the tangent, and the tangent crosses the x-axis at the new x estimate x est2. So then you draw the tangent from the point, so from the image of x est2, and then you plot the tangent from this point, and it crosses the x-axis at the new x estimate x est3, and so on. And you will see that, so if you were precise when doing your plots, you will be that the third estimate of x is exactly equal to the first one. So all the odd x estimates are equal, and all the even x estimates are equal. So I've provided a code so that you see better what's going on. So in that code, I have written the function handles for the arctangent function and for its derivative. And then, so I'm plotting the arctangent function between -2 and 2. And then I'm filling the x estimates. And I'm plotting the different tangents. So when you do that, you'll see, you can look after at the values of that are in the array x estimate, so x est, and you will see that every second value is equal. Okay, so let's move to the last question of the homework. So in 5c, you are going to use the Newton-Raphson method to try and locate the roots of the arctangent function. And you are going to use the Newton-Raphson function with 3 starting values. So one starting value that's just smaller than x hat, one starting value that is exactly equal to x hat, and one starting value that is just bigger than x hat. And for each call to the function, you store the root histories in 3 different arrays. And you compare, and thus you can compare the behavior of the root estimates. So, and this is what you have to comment. So if you want to visualize the roots, I suggest that you make a plot with 3 different lines corresponding to the absolute values of the roots. So again, using the semilog y function. And what you should see, if everything is correct, is that in one case the roots are converging to 0. In another case, the roots are basically constant. The absolute value of the root are constant. So this is corresponding to the case that you plotted in 5b. And you'll see that for the last case, the roots are diverging to infinity. So explain which case is corresponding to what, and also try to explain the different behaviors by comparing it with the plots you did in 5b. Alright, so this is what I wanted to say for this assignment. So I'm stopping the recording here, and I'll be taking questions just after that. Good luck with